Another day, another story. Imagine traveling from Vienna to Venice, your destination downhill, but obstructed by the imposing Alps. Chemical reactions, much like this journey, face energy barriers and terrain they must cross to reach their final destination. Today, we delve into the extraordinary realm of quantum tunneling, where particles defy classical physics to traverse energy barriers. This is the story of a groundbreaking study recently published in Nature. To comprehend quantum tunneling, we first need to understand the energy landscape that molecules traverse. It's a challenging terrain, and sometimes, reactions deemed favorable fail because molecules lack the energy to surmount the bumps. But here's where quantum tunneling enters the scene, allowing particles to tunnel through energy barriers, an idea previously forbidden in classical physics. In a revolutionary study published in Nature, scientists observed quantum tunneling in an improbable reaction between hydrogen molecules and deuterium ions, charged versions of hydrogen. This marked the first experimental confirmation of a theoretical prediction regarding tunneling in ion-involved reactions. The concept of particles appearing on the other side of an energy barrier traces back to Friedrich Hund in 1927. According to quantum mechanics, particles exist as probability clouds, extending infinitely. This means that quantum particles can theoretically pop up anywhere, including beyond energy barriers, where classical particles could never go. In 1928, quantum tunneling found its first triumph in explaining nuclear alpha decay. Since then, scientists have used tunneling to unravel mysteries in various fields, from semiconductors to the heart of stars. Yet, witnessing tunneling in chemical reactions proved elusive. Quantum tunneling reactions are rare and often slow, making them challenging to observe in the lab. Complex theoretical calculations limit predictions to simple reactions involving only a few atoms. With more atoms, it becomes increasingly difficult to calculate tunneling rates. The reaction chosen for this study, between hydrogen gas and deuterium ions, is simple enough for quantum mechanics to predict the reaction rate accurately. This is why the team selected it. They could finally validate theory with reality. Theoretical physicist Vyacheslav Kokolin and his colleagues predicted a reaction rate hundreds of times lower than the upper limit estimate measured previously. The initial discrepancy between theory and experiment left them hesitant to publish their findings. The root of the problem lay in the reaction's exceptionally slow rate. It took the Innsbruck team 15 years of troubleshooting to measure it accurately. They trapped deuterium ions in an electric field, exposed them to hydrogen gas, and chilled everything to 15 kelvins. At such cold temperatures, tunneling became essential for the reaction. The researchers waited patiently for about 15 minutes, which might not sound like much. However, for classical reactions, measurements often last for mere milliseconds, with nearly all ions converted. In contrast, less than 1% of the ions in this tunneling reaction converted into products. Tunneling occurred in only 1 out of every 100 billion collisions between hydrogen and a deuterium ion. This closely aligned with Kokolin and Yen's theoretical calculations, marking a remarkable discovery that thrilled the theorists. Tunneling reactions, like the one observed, are vital for chemical synthesis in the interstellar medium, where classical reactions are painstakingly slow. In the cold reaches of space, tunneling offers a lifeline, enhancing the chances of reactions in the ionized gas that forms new star systems. Back on Earth, this experiment validates the alignment of quantum molecular theories with reality, providing a benchmark for future efforts to unite chemistry and quantum mechanics. It opens up the uncharted world of tunneling and ushers in a new era of possibilities. In our classical world, reactions adhere to simple concepts, but quantum tunneling unveils a vastly different reality. Experiments like these bridge the gap between theory and practice, offering a glimpse into the extraordinary quantum world, where particles defy classical physics and usher in a new era of scientific understanding. Thanks for watching.